Welcome, dear students. This time I welcome you to another one more video on Riemann integration. This is lecture number 11. Actually, it is the continuation of lecture number 10, where we have derived this thing, that is the sum of or the lower these rectangles and the area of this whole curve y equal to fx. It is the curve graph of y equal to fx, which is bounded on closed interval AB. When we find out the area of this, it lies between, it is MR is this sum of rectangles which lie within the curve is less than the required area, but this area is still less than the sum of upper all the upper these rectangles. अपर रेक्टेंगल्स के लिए मैंने यहाँ पे वो रखा ये रेड वाला, लोअर में आएगा खाली ये वाले, तो अपर में आएगा दिस पार्ट एंड दिस पार्ट. तो आपको यहाँ सीधा लग रहा है कि इसका कुछ पोर्शन बाहर आ रहा है कि ये हमारे एरिया से ग्रेटर होगा और हमारा एरिया इससे लेस होगा. दैट इज एरिया इज कॉट बिटवीन ए एंड बी. मैंने वहां पे ये भी लिखा, व्हेन यू मेक द पार्टीशनिंग पॉइंट्स this tend to infinity, then both the lower sums and upper sums, sum of all the rectangles lower and sum of all the rectangles larger tend to area. Now we are coming to very important discussion. We have this, it is based on actually this. इसमें अगर आपको यहाँ पे एक्चुअली हम डिफिनेशन ऑफ द लोअर समज एंड अपर समज यहाँ से ही स्टार्ट करते हैं, लेकिन जब आपको ये चीज जहन में आएगा लेक्चर नंबर 10, आई मीन रिवाइज इट अगेन लेक्चर नंबर 10, उसके बाद आप आइए लेक्चर नंबर 11 पे, क्योंकि यहाँ में खाली डिफिनेशन अब देना है, तो ये आपको क्लियर हो जाएगा ये समझने से. ये मैंने दोबारा यहाँ पे बनाया आपके लिए ताकि आपको जस्ट टू रिकलेक्ट व्हाट वी डिड इन lecture number 10. You see how we start. We write, let us consider a function, let f of x be, it is a bounded, real valued of course, function defined on closed interval AB. Clear? Then you say it is bounded one, so it has the GLB and LUB. It is caught between the minimum and maximum. Since F is bounded on closed interval AB, we write let M be less or equal to Fx is less or equal to capital M. This is your GLB, this is your LUB, because you say it is a bounded. It is caught between the minimum and maximum. Then as usual, depending upon this, we write let P be equal to the set x0, x1, x2, x, you can take xi also, no problem, xi minus 1, xi. So you can take xr, I have taken in this case xr minus 1, doesn't matter, xr minus 1 comma xr, last but one point xn minus 1 xn, be a partition of closed interval AB. We take the partition of this as usual, such that, this is very important, x0 is less than x1, is less than x2, is less than x3, less than xr minus 1, less than xr, less than xn. This is your A, and this last x1 xn is your b. Okay, and we take a closed subinterval. We write let I of r be equal to xr minus 1 comma xr be the subinterval of closed interval AB. General subinterval, this we take the sub, because when we took R1, you will get the I1 first subinterval x0 x1, that is this. Then x, when you take R2, this is x1 x2, so this is a general subinterval. Since f is bounded, f remains bounded on closed interval AB, this implies it is also bounded on IR equal to XR minus 1 XR. In fact, it is bounded on each IR, bounded on I1, bounded on I2, bounded on I3. So in this closed interval subinterval where it is bounded, in this subinterval, on this subinterval, it has also the maximum and minimum. And we take the it is a maximum, the minimum there, GLB, that is we take it, let it be small mr, and maximum in this, that is capital MR. And accordingly we reach here, we define the what is called a lower Riemann sum and upper Riemann sum. It is nothing, it is the recapitulation of this. What you did in lecture number 10, we are just recapitulating it, writing it again, giving now the formal definition of lower sum and upper sum. In lecture number 10, I have just explained you how it comes, how lower sums and upper sums come, where from they come, where from they are generated. Okay, actually the aim is to find out the area, and later on you will have the fundamental theorem of integral calculus with the help of this, where you use the definite concept, definite integral concept for finding out this area. Here we are giving the elaboration of this Riemann integration, how it has generated. So we now define the lower sums and upper sums on this. Well, we continue. In previous step, I have told you that when f is bounded on the whole closed interval AB, and this is a subinterval, general subinterval, which lies in this is your ABI. So it is bounded on this interval, bounded on this interval, also bounded on XR minus 1 XR. So we write let capital MR and small mr be LUB. Capital MR is the LUB, least upper bound, or supremum you say, and this small mr is GLB of f in IR equal to XR minus 1 comma XR. You may write XI minus 1 XI or XJ minus 1 XJ, whatever you like as per your choice. Now we have this small mr as GLB of fx in this interval, subinterval XR minus 1 XR, and we have capital MR, the LUB of fx in this interval XR minus 1 XR, or running from this. Now we say it is obvious that m is lesser or equal to mr is lesser or equal. You can see, observe here. Here it has small m GLB of closed interval AB, and here it has capital M, this M as the this is, don't get confused, it is not MR here. Capital M, it has LUB on closed interval AB. So this lies in between this and this, because you have actually IR is contained in, is subset of I. It is a subset of Y. That is why this happens. M lesser or equal to MR, lesser or equal to capital MR, lesser or equal to M. Because this part is contained in this. Here on this whole closed interval, small m is the GLB, capital M is the LUB, and on this part we have the MR, small mr as the GLB and capital MR as the LUB. Therefore, this inequality will follow. It is contained in this. Now we define two sums. We define two sums two sums called a Riemann, called upper and lower R sums. Sometimes we write in short R sums, usually denoted by capital S and small s. We denote them by capital S and small s, like this. Capital S, we write it is summation of R running from 1 to n, capital MR XR minus XR minus XR minus 1, or this you can write also summation of MR delta R, where you have delta R is the length of this IR, which is XR minus XR minus 1. It is a positive length. It is positive length of the interval. And small s we denote by summation of small mr xr minus xr minus now. Now you are familiar. You know it. What does this represent and this represent? Rectangles. But usually this is also, you can write it summation of small mr into delta r. Delta r is this. We also denote the upper sums and lower sums corresponding to partition P of closed interval AB by this. We denote it UPF or UPFX, and lower sum we denote L of PF, or sometimes we denote L of PFX, one and the same thing. Therefore here you can write, you have now this thing, capital S, small s. This means you can say that this is upper Riemann sum UPF or U of PFX, upper Riemann sum. This one is lower Riemann sum LPF or L of PFX. Capital S and small s, initially we denoted by capital S and small s. Then for simplification, we denote the upper sums by UPF or UPFX, lower sums L of UPF or LPFX. This is just denote how you denote it. Okay. Now this is the definition of lower Riemann sums and upper Riemann sums. On this definition, with the help of this definition, we will be able to do more and more problems. But one thing you will always remember that your small m and capital M, small m is the GLB of f on whole interval AB. Capital M is the LUB of the closed interval of f over the whole interval AB. It is caught, it lies between this GLB of this and LUB of this, because this interval is the subset of this. We have two important observations I will share here. Two observations that you will remember. We will be using them in future also. Important observations is this. It is this. From this definition, observations. Number one is, since MR is less or equal to capital MR in closed interval IR equal to XR minus 1 comma XR, You have seen this here also. This is less or equal to this because this is the GLB, this is the LUB of closed interval AB on IR, and delta R is being positive. It is linked. You can multiply by delta R. It will not disturb this. This is MR delta R is less or equal to this capital MR delta R. If you put R equal to 1, 2, so on to n and add them vertically, and adding up vertically, if we add them vertically by putting this, what happens? What you give it? This gives you, when you give, what does this mean? This is your M1 delta 1 is less or equal to capital M1 delta 1. I am showing this at this setup because this is initial, and when we go ahead, I don't need to do like this. This is the initial lecture on this, how we prove that LPF is less or equal to UPF, and in coming lectures you will remember this. This is M2 delta 2 is less or equal to capital M2 delta 2, so on. This is Mn delta n is less or equal to capital Mn delta n. When you add it, you will get summation of Mr delta R is less or equal to summation of Mr delta R. That means you have proved that LPF is less or equal to UPF. For any partition of closed interval AB, our lower Riemann sum is less or equal to the upper Riemann sum. Okay, so it is a partition. We take closed interval IR, we add up this, we prove LPF is less or equal to UPF. One more observation, I have told you two observations I can write here. Second is corresponding to every partition of closed interval, we will be using it in future. Corresponding to every partition of closed interval AB, you may take the partition P1, you may take the partition P2, you may take the partition P star, refinement of the partition. There corresponds it is lower sum and upper sum. For partition P1, you have it is lower sum, upper sum. For partition P2, you have it is lower sum and upper sum. That is why we write corresponding to every partition, whatever the partitions you take, corresponding to every partition of closed interval AB, corresponding to every partition P, say it is P of closed interval AB, that is P belongs to the family of partitions AB, there exists lower and upper sum. You can find out the lower sum and upper sum, whatever the partitions you take. I have already told you in this previous lectures that partitioning of a closed interval is not unique. You can take different partitions. You can take the partition. For that I have explained the closed interval 0, 2 pi, and in certain cases 0 pi by 2, 0 pi. How many this partitions you can form? You can form in fact infinite number of partitions. So whether it is a partition P1, you have on partition P1 you have its own lower sum and upper sum. If you take partition P2 of the same closed interval AB, then you have another this lower sum upper sum corresponding to that partition P2. Say you take another partition P3, then you have on that partition P3 its own lower sum and upper sum. That is why I am writing this corresponding to every this partition of closed interval AB, that is P belongs to the family of the partitions of closed interval AB, there exists it is lower sum and upper sum. This is the definition of Darboux sums, lower sum and upper sum. Now you will have the terms very easily, you can understand them. Once you have understood small m, capital M, what does this represent? Small m represents GLB of F over the whole interval AB. Capital M represents LUB of M over the whole interval AB, because we took the F bounded. Then if we have the sub-interval that lies between closed interval A and B, it lies between that. then it has also the LUB and GLB. That LUB and GLB lies in between small m and capital M. You can observe it here also. This is less than this, is less than this, is less than this. So the greatest one is capital M, which is the this LUB of F over the whole interval AB. And remembering these tidbits, जब आप ये याद रखेंगे तो आपको बहुत आसान होगा अब इस ये थर्म्स करना और कुछ क्वेश्चंस करना. तो नेक्स्ट आई विल शेयर that is known as the first law of mean. Sometimes that is called the first law of mean. That is where we prove that these LPF and UPF जो है एक सेट का, एक क्लोज्ड इंटरवल का, एक फंक्शन का on the closed interval AB, lower sums and upper sums, the set of lower sums and upper sums are also bounded. Very interesting thing that is known as first law of mean. Very simple theorem, very short theorem based on the same. We will be sharing it very soon. Thank you very much for watching it, and you will enhance your logic and reasoning by reading mathematics and understanding it fully. Thank you very much. See you next.